In this class, we will learn about flanged beams. In the previous class, we have learned about singly reinforced beam, doubly reinforced beam analysis and design. Now, if we consider a rectangular beam which is continuously supported, like I've shown in the figure, a three-span continuous beam of different lengths L1, L2 and L3. When beam is casted, all the one-third portion of the spans will have positive moment, and at the supports we will have negative bending moment. Positive bending moment means the compression will be at the top side, tension will be at the bottom side. Negative reinforcement is opposite to it, which means in negative reinforcement, tension will be at the top side, bottom will be at compression side. So these flanged beams can be considered only in the middle third portion of the beam, whereas in the or near the supports it should be considered as a rectangular section. What is actually a flanged beam? If you take a look of figures which I have shown in the bottom, one is a rectangular section, another is a flanged section. A rectangle section is a section where the design of beam is done separately and slab design is done separately. There is no interconnectivity of the slab and beam structurally, which means there is always a gap between the slab and the beam, which I have shown there. Whereas in flanged sections, when you cast concrete in the beam and slab monolithically, monolithically means concrete is casted simultaneously both in slab and beam. When this happens, a part of portion of top reinforcement is embedded into the slab. This makes the beam as a T-beam because there is a monolithical connection between the slab and the beam. Whereas in left side figure, as there is no monolithical connection between the slab and the beam, this should be considered as a rectangular beam. And the right side figure, when you pour the concrete in slab and concrete simultaneously or monolithically, then the beam will behave as a T-beam, which means a part of slab is also considered the flexure resistance of rectangular beam. Whereas in the left side, only rectangular section is considered in strength parameters. So if you take a look of this figure, whatever I have shown here, in T-beams, concrete in the slabs is designed to take the compressive forces, whereas steel in the tensile zone is designed to take the tensile forces. So this type of a beams we often call as a flanged beams or also called as a T-beams. Refer Annexure G 2.1 for more information on flanged beams. This monolithical casting is very oftenly done in order to have T-beam effect. T-beam effect will not just save the material, it also saves the amount of steel induced into the flexural members. If you take a look of the pictures which I have shown in the left side, you can see that the part of rectangle section beam is embedded into the slab. This is normally done in very huge high structures where more ductile reinforcement is needed. And remember that only middle third portion of the continuous beams is considered to be as a T-beam, whereas Near the supports, it should be considered as a rectangular section due to change in the sign of the bending moment. Here is a picture of a typical T-beam. On the left side portion, I have noted 1, 2, 3, 4 and 5. 1 represents the compression flange, 2 represents the web steel, 3 represents the steel in transverse direction, and 4 represents the stirrups. In T-beam, the top portion, the slab is called as flange and the rectangle section is called as a web. I repeat, the top portion slab is called as a flange and the bottom rectangle section is called as a web. So we denote width of flange or width of web, or depth of flange or depth of web. We don't call here as a rectangle beam or depth of rectangle section. We denote or we notate all the dimensions in T-beam as in the terms of flange or web. Right side figure shows you the L-beam also. In the design and analysis of T-beam, the width of flange plays a major role. As I said in the previous slide, that the concrete is monolithically casted along with the beam. Some part of slab portion will be considered in the flexural strength of the rectangle section. The width plays a major role in it. If you don't have an accurate calculations of the width of the flange, then please refer page number 3637, clause 23.1.2. This clause speaks about the calculation of effective breadth of flange. In the figure, I have shown you with the letter B. This B should not be more than the breadth of web plus half of clear distance between adjacent sides of either sides of the beam. In the analysis of T-beam, there are three types of beams. These three types are decided based upon the neutral axis depth. The first case, the neutral axis is considered to be in the flange. When the neutral axis is within the flange, the stress diagram is considered to be in the flange only. Often, these sections shall be designed as a rectangle section. The same was also stipulated in G2.1.a in page number 96. When XU value is less than, greater than or equal to 0.2, or if XU lies just beneath the slab bottom, then the concrete attains the strength of 0.45 FCK and the stress in the concrete is uniform. This can only happen when your depth of flange is very small. And this condition is always taken as dF by d when it is less than or equal to 0.2, which is also stipulated in IS 456 page number 96. The last case, when the neutral axis is below the flange, then the stress diagram in the concrete in the flange is in non-linear. You can see in the figure. Whereas in the previous section, in the previous case, we have considered that the stress diagram in the flange is uniform. When dF by d is greater than 0.2, then the stress diagram is non-linear. In the calculation of moment of resistance, IS 456 stipulated that If the neutral axis is within the depth of the flange, then these sections shall be decided or shall be designed as a rectangle sections. The limiting moment of resistance can be calculated as 0.36 XU by D 1 minus 0.416 XU by D into FCK BD square. And neutral axis depth can be calculated as XU equals to 0.87 FI AST by 0.36 FCK BD. Now here we won't consider the breadth of beam. Here the breadth of flange is considered because our neutral axis is within the flange. So we substitute breadth of flange in place of B. Case 2 and case 3 moment of resistance calculations we will discuss in next class.